Good. So today we will be taking a look on structures. So for this we'll create a new project. Again, a console application. Okay, and the idea here is that until now we had handled machine types, so types which the CPU can handle natively and which can be represented and held in one register. A structure is a bit more complex. On the simplest way of thinking about a structure, it's just like a larger chunk of memory, which is structured in a certain way. And it can be handled to some extent as one thing. But of course, on the lower level, for the CPU, it is no longer one thing, like a variable that can be put into one register, but it's just a bigger block of memory, which is then somehow subdivided. So we create a struct with a structure of the struct keyword, and we can specify a name like my struct. Then we use brackets like this, and then we can specify which fields this struct will have. So for example, an int var a, and then we can maybe a int64 variable b, and a character var c, oops, and maybe a short, and maybe another character. Okay, and this thing, let's call it, can be accessed and used like one object. So we can use it as a type, for example. So we can specify the name as a type. Now we call it my var and semicolon to click it, to finalize it. And then if we want to access some of these variables, we just use the dot operator, which allows us to access the different internal variables which are available. And you can access them like a normal variable, so you can just assign something, or get something from one of the variables. So this behaves very much like any normal variable, just that it is contained within an object. And on the level of writing the program as such, writing the code, we can handle this thing like one thing. So for example, we can create another variable of type myvar, myvar2, and we can just assign myvar1, myvar1 has no one, myvar to myvar2, and the compiler will create code which will then internally copy all those variables one by one by one. Even though here it looks simple. So when we put a breakpoint, let's say here, we can compare how right, it doesn't like, because we have not initialized it, so let's initialize it first. Okay, so we see here that the compiler creates code which just loads from memory one variable into a register, and then it can save this register back into a variable somewhere. So it's as simple as it gets. When we see further down how such a operation looks when we are copying, or rather assigning a variable which is a structure, then here we see that it is quite a bit more complicated. So first we load the address of both structures into memories. We see here we load the address of myvar2 into rex and the address of myvar into rcx. Then we set up a few other things. There are two registers. There's RDI and RSI, which are used for repeated operations, which can be auto-incremented. So in principle, if we would want to save the code, we could here layer directly into those registers. There is no need to cache it into rex and rcx, but the generated code in the debug mode, of course, is not very optimized, so that's how it generates it. And then into the RCX register, ECX register. Well, it's the same. RCX and ECX are the same if you are using a 64-bit platform, just that you can specify how many bit you want to write to it. There is the size of this, or rather a count of steps. In this case, 18 hex. So that will be, what will that be? 16 plus 8, 24 is written here, and then we have here a move operation, but it is prefixed with this rep prefix, which means that the operation will be repeated multiple times. So we can watch the registers here as this happens. So let's step through it. So we load the two addresses into rex and rcx. I said this could have been omitted by loading directly into RDI and RSI. The data are now copied, and we assign here the value to this, and then to the ECX register. And then if we press on a single step here, we will notice that we are still at the same place. So the instruction pointer is not incremented, but the RCX register here, as we proceed, is getting decremented, and at the same time RSI and RDI are getting incremented. So in a way you can implement a loop, a very simple loop, in the x86 instruction set, just using as little as 4 instructions if you try to optimize it properly. So this gives you already quite a powerful tool to copy data. This rep prefix can be used with a few different opcodes, and as you see here, it's mostly used when copying things, and it is really convenient. The way it is defined, it requires exactly these 3 registers to be filled with the data, otherwise it will not perform correctly. And as you have seen here, the values are automatically changed of these registers until ECX reaches 0, at which point then the instruction point advances to the next instruction. So this is already quite nice. So such an assignment, of course, takes a bit more, but effectively in the end is quite efficient. Okay. So now let's take a look how such a thing is structured. So we have seen that the thing performed 24 copy operations. So first let's find out how big this thing is. Although actually we could take a look on the implementation here, and if we see that it says byte pointer, it means it really copies it byte by byte. So the size of the field should be 24 bytes. In principle, such a move operation could also work with words or keywords and copy larger amounts of data in one go. In this case, it is implemented just using copy single bytes, which is not the most efficient way, but it's good enough. Okay, so we know the thing was 24 bytes. We can quickly check it using the size of keyword. As you might remember, we had it already in the past. Let's call it const int my var with underscore my variable underscore size equal size of my var. We can use both, either the variable or the type. Both will work with the size keyword, and we see it tells us that it is 24 byte large. Now we can check whether it's plausible. So here we have 4 byte. Here we have 8 byte. Here we have 1 byte. Here we have 2 bytes, and here we have 1 byte. So in total 4, 12, 13, 14, 15, 16. So we have created a structure which, as far as we see it, only uses 16 bytes. But the compiler, for some reason, thinks that this whole thing is 24 bytes. And the reason why it thinks so is so-called alignment, meaning that the variables are not allowed to start at random offsets in memory. or rather you can make them start at random offsets in memory, but by default, the default packing order of a struct is to align the different types with their so-called natural alignment, and this means effectively that, for example, the 64-bit variable needs to be aligned to a 64-bit 64-bit 8-byte boundary. So here there is an empty 4 bytes which are not used. So we have like alignment here 8, another 8, and here those to have a full complement of sizes would add in total another 8, but we only have 4, so it adds at the end some padding of 4 bytes, and this then correctly represents our 24 bytes. So when creating such structures, one can of course try to be more efficient. If you know what you are doing, you can create a more efficient structure below. We'll call it a better memory alignment. And we will just copy it and reorder it slightly. So so we know we need somewhere 8 bytes. So let's say we move those 8 bytes to the very this we can leave to the very end. This will already help. Then we have, what do we have? Then we have here 4, 1, 2. This is not valid because the default alignment for this thing is to a 2-bit boundary, so we need to move this further up. Okay, 4 to 1, 8. This is this looks correct. Of course, we need to rename it my struct2, and we will now repeat the same thing. So my struct2, my var2, my var. Oops, how did that happen? My var2, my var2 size, my var2, and oh, this is 24. Ah, yeah, of course here 2. And now it is not updated correctly. My var2 size 4 to 8. That should be correct. Sure, that should be correct. We can run it to actually see what it does. Maybe it's sometimes the thing gets confused when we are copying too much. Ah, that's why it fails. We already have my var2 when assigning, that's why it's confused. Let's call it my var copy. Now it shows as it should 16 bytes in size. So such alignment considerations are quite important for multiple reasons. First of all, it allows you to actually save on memory. If you align your variables, if you order your variables in the structure correctly, you can save some memory at least. Maybe not huge amounts, but it can be significant. I mean, if you have a variable, a structure with a few dozen variables, and then you add, and then you make it such that you have a lot of padding, it might be up to 20% of your structure size, just empty space. So aligning this properly by hand is a significant improvement. And the more important thing is that to understand this alignment is that it allows you to use this structure across different systems. So when you for example save such structures to disk, and then on some other machine you would load the structure. Of course, if the other machine is like the same architecture, it will still make the same assumptions about your structure. But for example, if the other machine is an Arduino, and you have your C structure, you serialize it not to disk, but for example you send it over serial, and it's called serialization not because you send it over serial, but because you turn some object into a serial stream of bytes, which then you can send over a serial connection, but you could also send it over a parallel connection or something else. So yeah, anyhow, but the thing is, you send it to an Arduino, which is a completely different platform, which will have different not assumptions about alignment, especially also about data types. So as already mentioned earlier in the last lecture or the lecture before that, when you have a Arduino, for it an int will by default have only 16 bit instead of 32. So such considerations need to be taken into account, and also set the alignment such that you will end up with structures which you can then really move to other systems, transfer them, and then still be sure that they will behave correctly. It's also helpful, for example, when you want to use a structure to read, let's say, a file, or you have some file format. Usually those are not packed like with byte alignment in mind, but rather with space efficiency in mind. So so you can use this pragma pack instruction to change this alignment. So if you have something that you write to a file, you don't want to write empty space to a file, and you don't care really if this thing, when loaded into memory, will be memory efficient, or rather not memory efficient, but CPU efficient. So the reason why this alignment is usually done by the compilers is that a CPU can be used much more efficiently if the data is properly aligned, especially the CPU caches and memory access, etc. So if you would have a 64-bit variable, for example, here, which from inside your memory alignment goes from one 64-bit block and half of it is in another 64-bit block, then effectively your CPU would need to load both blocks into the cache and then pick the right portion out of it. So it's quite obvious that if the data is properly aligned, the CPU can save on operations if it can load the variable in one go into one cache line, because first of all it needs less memory operation, and secondly it is using less cache. So both aspects improve performance in execution. Of course, you pay by using a slightly higher amount of memory, but usually this is very much justified. And if you want to change this, you can use this pragma pack1, and this will make the structures which are defined below it packed with 1 byte alignment. So as you see here, this changed our previous structure, so it basically removed those empty spaces and it made it just 16 byte like the other one. But of course the performance was negatively affected by this change, and usually this is not something that would be really recommended to be done when you are working reasonably with your system, but because I said it really impacts the performance negatively. But when you want to use structs to load data from a file, this is quite a convenient approach that saves you some headache to manually, for example, then change this. And what you also can do, if you want this kind of to be undone, so if you don't want this to affect all the structures, you can pack push command use it like this, and if we so this kind of undoes. So with many of these pragma instructions, you can use this push pop architecture to undo whatever you did. So let's call this thing 1. So now this, we see the size of this one, and this is again 24. Now we can actually check. If we take this one, then it's 16. If we take the other one, which looks the same, it's 24. So this is on the first here for correctness. Then those data can be removed since there is no padding there. So this is something you can do. You could also enforce some other packing order, but usually you only want either the natural one or the one byte aligned, which is then suitable for file operations. Okay, what else? Of course, when you define variables, you would like to be able to initialize them somehow, to assign some values. So as we have seen, of course, you can assign the values to the inner variables like one by one, but there is a more efficient way which you can do, which from its syntax is similar to how you do it with an array. You just use the curly brackets and then you write the values in the same order as they are defined in your struct, and they will be then applied to the individual struct members. So when we run it again, we can see here now that our struct, all the values have been correctly initialized. Now, of course, since the structs here, this one and this one, while they have the same member variables, they have them in different places, so they are of course completely incompatible. This is of course something to keep in mind, that we are really just handling a memory block and offsets within this memory block. On the level of the machine code generated by the compiler, there is no understanding of the name of the member variable. There is really just the understanding of which offset, and the names are kind of just helpers for the human developer to not work with offsets, but really just be able to use variables. In principle, if you would want it, you could just define a byte array and then access it at different offsets, and you would need to remember which offsets you have to access and which size of data you have to access. So this really is just kind of a convenience feature, but obviously such convenience features are in fact extremely useful when programming. So let's see. Another thing you can of course do is you can get an address of a variable. So let's do that very quickly. Meist asterisk p var 1, 2 doesn't matter. Yeah, let's go with we use the reference operator, as you remember from pointers that we had during the last lecture. And now we just obtained the memory address of our structure. And if we have the memory address, we can of course access the member internally. So of course something kind of obvious that it works is that let's call it maybe this that's what it was about is that you can in principle use the asterisk operator to dereference the pointer. So and then we can use the dot operator as we saw here to access var b, but this is kind of cumbersome. So there is another nice thing, the arrow operator, which combines those two operations into one. So the arrow operator and the dereference dot operator are in principle equivalent, but this is kind of more convenient since you have to type half as much with regard to the dereferentiation itself. We can put a breakpoint, and we'll see it in the generated code. As we see here, both versions generated the exactly same instructions, so they really are fully equivalent here. And you would almost always use the arrow operator. This is something you can do. You usually would not do that. Okay. Any questions so far? No questions? Okay, so let's continue. So what we of course also can do is we can, for example, create a pointer on a struct, which in some cases might be useful. especially when passing things to a function. Such a pointer on a pointer constructions are usually quite convenient. Let's call it pointer to variable 2. So this thing would then be just no, this was var1, then let's keep it at 1. Then we just do it like this. So basically you can take a pointer on a pointer on a pointer, and this should not be 2. Needs of course to be the right type. And on the pointer and so on. So you can have there is no like natural limit to how many pointers and pointers you can define, but functionally it doesn't usually make sense to have more than a pointer on a pointer. And the idea, for example, with functions, which we will be taking a look at later, is that you can give a pointer on a pointer to as argument, and then you have some variable which is a pointer on a pointer, which address you gave to a function, and then the function internally can change the value of the variable of your pointer. For example, allocate some memory, assign it a pointer, then write something to it, and then once the function is done, you end up with having a valid pointer on something that you can do something with. So this is where this pointer on a pointer constructions are useful. Also, when having such pointer on a pointer situations, you end up using this this is asterisk operator actually more commonly. So for example here, so we have a pointer on a pointer. So you cannot, at least not reasonably, use like this. That doesn't unfortunately work. So what you need to do in such a case is that you first asterisk dereference your pointer, and then you can use the arrow operation on the pointer was pointing to, and then you get your data. The other approach, of course, would be to repeat the dereferentiation twice and then use the dot operator. That gives you again a functionally equivalent code. We see here that the generated code, once we go to it, is longer, of course, than in the previous case, since we have now one more level of dereferentiation. But again, we see that those two ways of writing it are functionally exactly equivalent. Okay, so now what we also can do with structures is we can create nested structures. So we can create a struct x. It's kind of in the Windows world common to use the X extension for something extended. It comes because a lot of APIs, when moving from the 16-bit to the 32-bit Windows version, were called something X. And then, of course, if people often use it, then it kind of becomes a natural approach to it. Of course, it only works like kind of once, so you can use X. If you want to have something that is extended again, then you just write it something like my structure 2 or max. You could just write X orXt, but then it's not clear which one is the extension of which, so usually this would not be that much recommended if you have more than one level of nesting. Or you could have like a completely different name. So you could have like my base structure, and then you would have my specialized structure for blah blah, like a longer name that specifies this. And the way you create those is quite simple. You just take your structure's name. Oops. You basically can treat any structure like a type. Even though it's not a machine type, you can treat it the same way. You can use copy and so on. So the compiler will generate the necessary operations. We can also try a compare later on, how that behaves. Right, so we write here a structure as the, what do we call it? Let's call it stx. And then we can add another variable, like an int64. For example, a var f. Yeah, we'll add e. Add e, so the next one is variable f. And now, what we can do maybe here that would be also quite helpful as we write down how such a structure actually looks like in memory. So, think I have not enough space, we'll see. So we need free space, I think, for it to look nice once we are done. Okay, so the first one goes from 0 to spaces until 4, and the other one starts at 4, and we of course don't have 9. It goes to 8. Actually, it goes to 7 since we started at 0. Then yeah, then this one is also no, this is, yeah, 1, 2, 3, 4. It's the same. No, it's not quite exactly like they all the same separation. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1. Okay, no, it's fine. And this needs to be, of course, now correctly aligned. Like this. And the 7th, it ends at 7, so then there will be no more room. So this will be then var A. It contains the bytes 0, 1, 2, and 3. And var this is empty. But it's not quite centered. I will make it look pretty later. That's a waste of time. Okay, so we have var 8, and we have here our 64-bit variable var b. Then we have our var c, and d, and then we had e. Okay, and then again an empty space. Okay, then we copy that. Do the same here for this one. Just that we moved those stuff upwards. Just moved it in here. Okay, I somehow somewhere have one space not enough for the thing to be nice. Okay, actually fine. Then we copy this again. No, so we copy this again and go to our struct x. And our struct x will have basically the same alignment, just that here will be the var f added. And from this, what we notice is that if you're only interested in the first five variables, then it kind of doesn't make a difference whether you have a struct x or a struct. In memory, it's the exact same thing, and this is something that can be quite useful. So first of all, of course, let's define again our new struct. So we are lazy, so we copy struct x var x or var free. Let's call it var free. Var free, var free, var free. So we had 24 plus 8 makes 32. Makes sense. So now our structure is 32. Our new structure, our bigger structure, is 32 bytes in size. And there is, however, a bit of a caveat with that. Well, not with the size, but with how you can use such a structure. Because if you see the dot operator, you see only the two members that it has. So you see struct and you see our var2. But if you want to access the members of the other thing, you need to use this dot operator on the sub member. So let's assign all the values. 2, 4, 5, 6. Okay, it was one too much. That's A, B, C, D, E, F, and F complains because F is on the main structure. So while you can nest them quite nicely, like here, effectively, of course, this will here cause you to need to address this sub element. So one thing, for example, that can be done if you want to simplify your code is you can create a second structure. Let's call it structure X, and then just copy the content of the previous struct definition. Let's shift it somehow while copying. Alright, yo, I also forgot here. You want to, that was 24, and this is 8. Just always, let's say how big it is. So we copy this in here, and 8. And now this thing, let's repeat it. Those steps. This is the number 4, 4, 4. 4, 4, 4, 4, 4, 4. Now, of course, you don't have the sub object, you have just what you had before, and you can access it much easier. And important is that this thing and that thing in memory, they look exactly the same. So this brings us already to the next trick that we can employ, which is, so we have our variable, this one. So what we could do is we can create a new variable of that type, or let's say a pointer. This is equals reference to this. Of course, now it complains because the types don't match, so the compiler knows, okay, this is my struct X, and it's not like smart enough to look inside and see that it actually is identical to my struct X. It just sees that it's an incompatible type, so it complains, but we can force the cast, and then we can basically use the other representation of the same structure. Of course, this is there is a purpose why the compiler is complaining, because this is in as far dangerous as if you change our struct here, then the change is automatically propagated to struct X because it's using it, it's referring to it, and the compiler knows what to change. But here there is no auto-propagation, so at this point, if you would change the previous structure, then the struct X would not longer be aligned with it, it would be different. And then, of course, accessing those member variables would cause troubles. So here, to avoid such problems, the compiler will warn you. Now, what you also can do is, well, pretty much the same thing. You can have a mystruct, let's do it however further up. So we defined here our mystruct X. Let's play with it. So we can define a pointer to mystruct X. That is then 5. Mystruct X. And here we assign just oops. X. No, not here. So basically what you can do is, if we have my var, which is here, well, smaller, it is, as you see, it's only the 24 byte, you can still assign it to a pointer of my var X, and you could here be accessing like this, or maybe actually, you know what, let's move that further down. It is a more convenient test case if we do it here. Plus then the numbering is correct. So you can here still access, yeah, then use the X as well, not the X, for convenience. So then you can still access all the members, but the last one, you can access it, but it won't be valid. And depending on how your program is structured, it might either crash instantly, which is rather unlikely, or more likely it will just corrupt some memory somewhere else, and then you have a problem. So to exemplify this, we have here defined our structure. Then we have this int, which actually might live here. With consts, it's always never guaranteed where they will live, but since it's a debug bit, it's likely to live there. So let's just remove all the breakpoints and assign here a value that we notice 0, 1, 8, and let's run it. My var 3 x one of them is not the right. My var 3 should be fine. We take a reference on that and then we cast this 2x well, the compiler knows that this is not the same thing. Let's quickly see if it accepts the other one. We reuse the name for some reason, because normally this in the different levels of indirection you get if you are working with like when you have types, when you're casting from a type which is not a pointer to a type that is a pointer. And this end should actually give us the. Also, it works for some reason perfectly nice with the other one. It must be some very trivial bug. My stroke tags. Do we have? Was this? That was already. This name was already used. Then this needs to be 5, and the other one will be 6. 5, and this one will be 6. It kind of threw an error which was kind of throwing us off. So we kind of tried to assign value here, and we see of course that it actually looks even correct, but obviously our structure here only has as many fields, and we have written the 1, 2, 3, 4, 5, 6, 7, 8 to somewhere else. It's not guaranteed that we actually will find where we wrote it to, because apparently it didn't end up in the const variable, although size of that is 18. So let's actually here define on purpose a dummy variable. It being defined as the next thing after our struct should be more or less the natural place where such an operation would then end up putting the data in. It still doesn't work. Let's see what the offsets are. So of course, since this is a debug build, it might add some spare space so that it can try to find such thingies. So let's see. So my var lives at RBP plus 8. This is where my var lives. Let's clear that. And dummy1 lives at RBP plus 38. That is definitely far too much. So the important thing to also to keep in mind here is that this order of placing of variables, it's defined within structures, but it is not defined necessarily in a strict way within a function. So when you create variables in a function, you can somewhat assume that they will be in the same order in which you created them, but the compiler might reorder them as the compiler sees fit, and you cannot make any assumptions about this. So in this case, we have seen here that even though the variables were defined one after the other, we had, it was 24, so it should be 24 plus, it should be hex. No, decimal is fine. 24 plus 8, so the next variable should be 32, but it for some reason put our variable here at the offset 38. Also, this is 48 hex, so when you go to hex 38 to decimal, that's at offset 56. So there's quite a lot of unused, unallocated space after those variables. So we kind of cannot easily catch this right attempt. Of course, if we would added more variables here, actually we could try to force this. So we said right, so what we where were we? So 24 plus 8, that's 32. Let's copy this. So go to hex we want 38 to decimal minus this divided by 8. So we need to have 3 more variables that will help us break things even more. Let's call it like this. So let's go f GHI. Then we do the same here. And then we of course fix our structure information f GHI. Oops, E, not O. And if I'm not mistaken, writing to I will now overwrite our variable. I would not assume that the compiler will change things. So we can see here it is still 8 and 33, so it doesn't change things that it already kind of made a decision on when you change things in the function further down. Now we have overwritten some memory. Let's see if we overwrote the right offset, and voila, we managed to write to the dummy variable which we have created here, which obviously in this case was intentional, but you can see, I think, quite illustratively that if you would have a complex function doing things, then you would just override some of the other variables which have other purposes, and that would make your function behave in a completely unpredictable way. So that would not be a good thing. And with C++, as you have seen, I think, by now, and somewhat realized, it is it can happen quite easily that you do something that might end up causing trouble. So it really is important to be careful and to know which things are safe to do and which things can only be done with utmost caution, like casting, like forcing a typecast. If you know that it will be fine, then it will be fine, like with the case above here. Because here we are forcing the cast, but here we have in our second structure the same variable, so we know that the thing will behave. And with the other, where we are forcing the cast here, we know that well, in this case we know that it will misbehave, and we can even predict to some extent how it will misbehave. Why in this particular function the compiler left 3 empty slots between those two variables that only the compiler knows, well, and the people that wrote it. If you would be compiling with GCC, the result would be completely different. Or if you would even be compiling with MSVC, but a much older version or much newer version, then you could also expect that it probably will behave in a different way. So this is not something you can rely on. So let's write this as a comment. Should I write the line number? It may change. Let's not write the line number. At the beginning of the function. Okay. So now, is this something you should never do? In fact, no. In fact, this is something that Microsoft Windows does a lot. Because if you have, for example, again, I'm grappling here a bit in the future with functions. You can have a function which takes a structure, rather a pointer on a structure, as an argument. And what you, for example, would want from your APIs is the ability to extend them. So you would want to have a function that takes a structure as an argument, and then it has some members which you can set with parameters. Since this is somehow more convenient than to have a function which takes 100 parameters, it's nicer to instead have a function which just takes such a structure, and then you can set all the parameters you want. Plus, if most of the parameters can be set to 0, you could use a function called memset, which just zeroes some amount of memory, and this is extremely efficient since on many systems this is on many compilers implement this as a compiler intrinsic, meaning that it really just in the place where you use it, it just generates a snippet of code which zeroes everything. So it's as efficient as it gets, and then you just set a few values, and then it's much less typing than if you would need to write like 20 arguments, of which 18 are 0. And the way this is made to work in case of the Windows API is that you have the first variable in the structure will be, for example, there will be a size field. So let's make a demo. let's do this here. So we would have a, for example, stoked as my API v1 API stoked on my API param. That's a nice name. My API parameter version 1. Then we have a size t. Size. Then we would have stuff. Let's just go with this much. Stuff doesn't matter. And then what you do is you define your oops. My API param version 2, which contains the same stuff plus more stuff. If I may make this pawn. Okay, suck. And now inside your function, which you are calling, inside your API function, you can just look at the size. So usually the way you would use such a structure is you would define param1, or let's say with v1 is equals, then you use the square bracket operator, then you use size of. And this, in fact, as we have seen with the arrays the last time, will not only assign a size of the thing itself to its usize, but will also automatically generate code to 0 all the other parameters. So now you just need to set the one parameter you care about, and you are ready to put this somewhere to use into and send it into a function or something like that. And of course with version 2 it would be like the same thing, just that semicolons missing. Just now you can set not just f 1, 2, 3, but also g as well, or the other ones obviously. So, and now of course if you pass this to a function, and the function would need to check which version of the API it has received, and internally a reasonable, a safety conscientious way of doing it would be that the function checks the size and then either calls a function like my API v1 and passes to it the v1 parameter, or calls another one my API v2 which passes the v2 parameter, as to avoid the risk of some improper casting. The insecure way of doing things would be that you would just have a lot of ifs which would then check. So example, do something, let's say we get our here as a param. So obviously your API function would use the newest version of the size, my param, my API. Let's go like this, but let's give it only the reference, so I point down the older one. So let's say our to do is like int sum is equals 0, then sum is plus equals, so let's be lazy. Oops. Plus equals 0, my param API f, and if size is greater equals, because you know you might have a version 3 and version 4, and as long as you only add parameters and never remove one, so you might have a situation where you decide, okay, this parameter is not needed anymore and you want to remove it. If you want to use this pattern of creating structures for APIs, you cannot remove it. But you can, for example, rename it to unused or reserved or something, so that the space is still consumed, the alignment of the structure remains, but the name, which is meaningless once it's compiled, indicates to the developer or the user of your library that this parameter is obsolete or unused or reserved, or basically that they should just leave it at 0. That's the short story I want to say. Okay, so you check whether it's greater or equals size of my param2, and if it is greater or equals size 2, then we know at least until there we have thingy, so we can then add g, and we can we could add the other one. So this obviously is a kind of boring function example. It just first of all, this would of course be in a function, but it just, you know, sums everything together. It was, at least that would be the idea if it would be fully developed, and then would return, let's say, the sum of all the fields. Not something particularly useful, but I think it demonstrates quite nicely this programming pattern where you are checking the size field. Now, technically, the size field just would need to be somewhere within this version 1, but as we have seen, it is quite nice to have it at the beginning, because then you can initialize the whole thing to zeros and with the right size with inside the first line where you define your structure. So this is quite convenient. And yeah, and that's that. Are there any questions? Okay, no questions. Okay, so other things which are worth mentioning is, of course, you can get a reference, let's go with int64. You can of course get with any of those structures. So let's go back to our which one do we like? Let's go with this one, var3. Reference var3 6 b, no, not b, f was the 64-bit. Wait, isn't there an f? Why is there an f? B. Oh, wait, this. Oh, it was b, not f. F was then defined later on. Wait. So this means right, f was already defined here, so this means that my example here is actually invalid. That should be b, and that could be f. Yeah, okay, b and right, so we already have seen here that I kind of accessed a member from the here it was actually valid because I had the f here. Okay, now sorry, then it's fine. But it would be very easy to accidentally if you are doing it like this, it would be really easy to accidentally access the wrong member, and then you would have troubles because you kind of tried to read memory which is invalid. But as we have seen here, usually you will have some memory in the space of the memory that is kind of invalid for the context of the structure. So especially if you are using read operations, there is very little chance that you would find this bug through an exception or something. You would see, okay, the thing, for example, if it would be mostly zeros on our example, then you would not even notice it if you read a field too much, because you sum in zero. But for example, if you would have a sum code where in this place where there mostly are usually zeros would sometimes be something non-zero, then you would notice that your function sometimes returns the wrong sum. And why does it do it? And in this case, obviously, because somewhere the if was in the wrong place, or then you forgot that one of the variables is in the other API version, and then you accessed it accidentally and read some random data from somewhere else in the computer's memory. So this is something to keep in mind. And as said, the more cleaner approach of doing it would really be to dispatch then so either you could of course have like just a large if block in your function, and you cast on the type 1 if you have the type, if you see that it is type 1 or rather version 1, or that you already have functions which dispatch it and then handle it independently. The downside, of course, of this secure approach is that it to some extent might create redundant code depending on how many changes you have in your structure. So another approach which would be quite reasonable would be to make, for example, a copy. You always inside your function, which by default handles the myparam v2, and then what you would do is at the beginning of the function you would always copy it from whatever type it is So you can make an example for that. So data implementation, it's complaining here, my API v1, right, because this of course is v2, so this needs to be casted. Okay, so here we are inside the function. So what you would do there is you would have a variable v2 my param copy. Let's do it differently. Let's make a second that you have your copy variable, then you check if variable size is equals size of v1, then what we do is now is kind of a again the usage of pointers in casting. We want somehow to copy it. We could of course you could of course use memcopy, which is a function, but since functions are the next subject, and technically we are not aware of how to use functions at this point of the lecture, we won't use the memcopy. We'll use a different approach, which also is kind of more fun. So we have here our thing, which is of type v2. So we take the reference of it, we cast it to v1, and then we dereference the whole thing, and then we just reassign our input was this one, but that will of course also not want to allow you to assign, because this is technically a v2. I mean, both are v2 at this point, but they are missing values. So we cast the thing to v1. I think I need one more bracket. Yes, no, the bracket is not needed. I need a differentiation here. So effectively, this creates such a copy code as we have seen before, but it will only, since at this point the compiler was told that those memory blocks are v1, then it will only copy as much bytes as there would be in a v1 structure. And then of course you would need to fill in the rest. So you have your copy, and then you know that I think f was there, g and the others, g is equal 0. Or you could of course use a different values. You don't need to use 0, f, g, h, i. You could, depending on the semantics of your structure, like just pre-fill default values if you want to do it. But usually the reasonable approach would be to use like zeros as the default value. But it really depends on the semantics. I think speculating here how you could do it is pointless. It really is up to you. But you would generally just need to ensure that your data is full. What you also could of course do is alternatively you could pre-fill your copy with just 0, which would also set size to 0. So then you would not even need to zero those explicitly, and it gives you a much nicer code. Then of course you make an else branch. If this is size of 2, then, well, actually if this is a size of 2, then it's kind of easy because you don't need to do anything. But cast operation wise, except one dereferentiation here. But of course if you would have now like a version 3 and a version 4, then you would have more branches here in the if and more castings. And then for example you could check if this is size is 0, then you just return some error, because it means that whatever was passed to you as this object, the size, you are not aware of the size. Or you could also, of course, here define it that you accept any newer version, that you say, okay, if it is larger equals v2, then you kind of will just handle it as if it would be v2, and you will just ignore the additional parameters which are there in the memory, which your current code is not aware of how to interpret them. So it's really a flexible way of doing things. Then this test 0 would still be meaningful, because everything that's smaller than version 2, it still validates whether the size is correct. So it would not catch the case when you pass some random garbage which then accidentally makes the size field bigger than version 2, but at least all the other cases where it would be less than, but not a valid structure size, then it would bug out. you could also have like a handling then that if in this case it prints an error message like a neural structure passed, variables ignored, and then not the error, maybe let's call it a warning message. And then if your application would be to misbehave at some point, since you get such a warning message, you would say, okay, but this structure passed there is not exactly what the thing was expected. Let's see what is passed there. Maybe it's garbage. And then you, it would give you like an hint where to look and where to try, how to try to fix the issue. Okay, so and of course, as said here, you can access also any sub-member of your thing and get direct pointers. Basically, as said, the thing is a memory block. You can at any point in time generate a pointer or on anything you want to. And the last thing I think that would be fun to demonstrate would be what I said a bit earlier, that in principle such a thing is just an array of bytes. So my struct1 which is var here. So we could define char my both 24, and we can my both is equals my var, which of course the compiler won't like, but we can, so this already pointer type, so we can okay, it does not like to us. If we don't have a bug in the code which is very severe, we can just press F12 and it brings us to the definition. But if the code is too broken, it fails. Right, so we do this. So yeah, so we have here a array which effectively behaves like a pointer. It feels like a pointer. It's not exactly a pointer, but the next best thing. So we just cast the pointer type to a mystruct, and then we dereference it. Oops. And then we use assign, so then the compiler will create the particular one. Why can't I disable the breakpoint? Oops. Okay, now it's gone. Let's run it. So, and the code will just copy whatever was in our, as you see here, it copies whatever, it's the same copy code as if this would be another mystruct instance, because as said, if we tell it that it is, then the compiler assumes, so the compiler always believes what we say even if we are wrong. This is something that needs to be kept in mind, and again, one of the great many opportunities to do something really unsecure or dangerous with regard to to your program. So just be careful what you tell the compiler, because it trusts you unconditionally, which is not always the right thing to do. And also that said, other compilers might be much more restrictive. So C++ simply gives to the developer all the opportunities to do all the mistakes. Other more modern programming language are more like assisted programming. It takes you by the hand and it kind of tries to help you not to break things too badly. Okay, so we can do this, and then let's copy our thingy. So copy our instruction guide, that we know where to expect what. Zack. So we also know what we have copied in the variables, like 1, nothing, 2, 3, 4, 5 was copied into it. So these are the values we expect to be able to retrieve. So we define those variables here outside, or actually we could use, oh, that's a nice idea. Let's grab the other struct, the struct2, which has a completely different alignment. It's the more memory efficient one. So obviously first things first, if we do my struct2, my variable 2, that was definitely used, 7, 8, 9, 7, yeah. Right, so we have this thing, and then we kind of just do the same thing here. We just kind of force it to copy, but let's at least not trash any memory, and of course we need to take a reference on that. No, we need to, that will be annoying. Let's do it differently. So this stays as, oops, this stays as is, the other one we take the reference. So if we would do it like the opposite way, with my struct without the 2, then we would use the bigger struct and copy it in the smaller struct. So we would even overwrite some memory, which we don't want. If we do it this way, we at least don't overwrite any memory that we shouldn't. But it still won't give us the right result. So when we inspect my var, as said, it contains... oh, I overwrote one of them. I overwrote variable b with 1, 2, 3. 1, 2, 3. Okay, let's leave it overwritten. That's fine. So I said these are the values that we expect. We said 1, 1, 2, 3, 3, 4, 5. But what we got is 1 garbage, garbage, garbage. 3, 4, 5 accidentally happened to be at the same place. So as you see, that's not how you cast from one type to the other. The structure of those structures must be compatible, otherwise we end up with literally garbage. So how do we do that correctly? So that this is very, very, very wrong. But we still are motivated to get the data into our variable 4. I should maybe move this up there. And of course, like the boring way of doing it would be var7a is equals punct a, and then we just keep on going. A, B, C, D, E. I think that's all of them. B, C, D, E. That's the correct way. That's the correct way. Boring. But now if we inspect our var7, var a was var a 4? Shouldn't that be 1? Var a is 1. Oh yes, here a b c. Yeah, we have. I skipped a line. Okay, so extra. So var a is 1, var b is somewhere else is 1, 2, 3. 1c is 3, 1e is cd is 4, and e is 5. So as you see, obviously this works. I mean that was to be expected. That's trivial, but as I said, it's kind of boring. So we can. I mean, this is the correct way, and it's the only way you should do it. The other way we will do now is just like for fun and nothing else. Okay, so as you remember, we have assigned our variable here to this buffer. We wouldn't need to copy it. We could also use char asterisk and then just cast it. But let's use it with a full copy. So, and we have here our cheat sheet. So variable a is at offset 0. So that's as easy as it gets. So that's a pointer to int asterisk buffer plus 0 and asterisk. Good. The next one is empty. The next one is int64. So asterisk int64 asterisk, and the offset of this thing is buffer plus 8. So I can write this here maybe for cheat. So this is then, well, this is at 0. Oops, this starts at 8. This starts at 16. At 16. It's 0 at 8 x 16. So this is plus 8, so this also is easy peasy. C is a char, so we can just directly we can keep with this I mean oh, let's be fancy. This is a char, so we go and it's 9, and the other char will be 9 plus 3 is 12. Wait, 12, 9 plus 3, it's 12, yes. Receive this code. And here we have the short asterisk. Did I not miscounted something? 8 plus. Oh yes, no. Plus 8 plus 9 should be fine. Yeah, should be fine. Right, short, and then we do the same thing, but we of course need to add the right offset. So we had at 9, this will be at 10. That should be at 11, because 9, yeah, that's, now it's correct. It should be just plus 2, because we only want to shift by the other 2. So we take at 9, here at 10 and 11, no, 10 and 11, no, then 12 was correct. We will see. Is E? No, it's not correct. Which one is broken? B is fine. E. This one is not. This one is not fine. So this is 0 till 7. This is 8 till 15. Ah, sure. This one is 16. 16. This one is 17. And this one is 19. Now it's correct. A small boneheaded mistake, but as said, doing such things is error prone. Wait, no, it's still wrong. Wait, so C is correct. C is correct 3. C is 3D. 17. Should be. It's shifted by. Was C3? C was 3, D was 4. Okay, 16, 17, 18, that should be correct, but it's not. It seems like, wait, this doesn't make sense, that should not work. Yeah, this is garbage. Over plus 17, 16. We take the 16 here, we take 16 and 17. If I just shift it by 1 in the other direction. Wait, is this differently aligned? It should not be differently aligned. Let's inspect our buffer in memory. Because this is a copy of struct of this struct. And the struct is C, D, E. This is the order that should be as it is. So we have first our 1, then we have well, unused. Unused is when you have a debug build initialized with Cs. This could be disabled, or in the release build it will always be disabled. Okay, then we have 8 of the other ones. Then we have 3. This character. Then we have another character. It is differently aligned. Ah, damn it. And then there are just 3 C's at the end. Well, that makes sense. That makes sense. That make all the sense. This makes all the sense. I told you bullshit. So the compiler of course tries to correctly align D as well, so it adds some empty space here. And E, since it's a char, it's just attached at the back here, and then we have just 3 unused bytes at the end. That will need some correcting. So this is wait, but why does this then worked? Because in this case, this thing shouldn't end up by 16, because it then should have shifted the whole thing by 1 more. And Did I break something with the padding? No, I changed the order here. Sure. I changed the order here, that's why it's correct. Var A, var D. Yeah, that's fine. I just wrote I did it correctly, but here I just wrote it down, not how it should be, and then I propagated the error. Further down. So here and there and there. I mean, once you think about it, makes all the sense in the world that this needs to be aligned this way. Just sometimes it's easy to forget things, right? So and what we also can do, just for make it slightly different, is you can also use this semantics instead of this one that gives you the same address, but as we have seen in the lecture about pointers, the compiler generates sometimes slightly different code, even though the meaning is the same. Okay, so let's run it and then see 1, 1, 2, 3. In hex it's 7b, 3, 4. Wait, C is 3. Y is 4. Yeah, 3. Just move. I'm not moving enough. 4 and 5. So as you see, this is probably the most definitive English word for that demonstration that really the whole struct is just a buffer, and you can really access it just like a byte array and extract the data. Of course, this is extremely inconvenient since you need to know the exact offsets, but this is just like code-wise, this both of those approaches effectively should generate similar code. Maybe not identical code, but similar code. We can take a look on it, and so as you see here, it's always like just 2 instructions with offsets, and it's copying. And here we had 2 instructions. We have 2 instructions. This versions here needed a few more instructions, so it isn't not as efficient if we kind of do it by hand, so to say. But what we have seen is actually that using this plus notation. So let's if we switch this back, so I will leave this here as a comment. 18 plus 18, and here we can change it also to the asterisk of plus 16, and here asterisk of plus 20. Now when we have the pointer arithmetics, we don't have the square bracket operator, and now we get the exact, is it exact? At least very close. No, it's exactly exact. The exact same code as we get when doing it like this. So the thing to learn is that we've already seen in the pointer lecture that the square bracket operator, even if it semantically does the same thing, it at least in the debug build introduces additional opcodes. But if you just use the dereferentiation and the pointer arithmetics, where we just add the right offsets, then we end up with the same code as efficient as we would be doing this here. And of course, this is the most efficient way how this can be done. So if you have 2 structures which are not compatible, so that you cannot copy them directly by assignment, then this is the only way how you can do it. Okay, I think this is enough about structures. Are there any questions? Is everything clear? Okay, no questions. then it probably is clear. Then let's continue. So this covered well structures, but there is another thing which is somewhat similar to structures in C, which is called a union. So as we have seen, the structure, it is a memory block where multiple variables are grouped together into one block. A union is quite different, so let's define one. My union, and let's give it something to do. For example, you could use one thing about structure I didn't tell you. You don't need to like copy like nest structures like this. You can just write struct and write another struct inside this thing. So you could have like a struct st_, let's call it like this. This of course breaks something somewhere, because we have accessed that definitely at some point. Semicolon is missing, of course, as well. And we need a name for it. No, sorry, so let's call this sty. You can also create an anonymous structure if you don't give it. You don't need to give it a type name. You can just define it like this. So basically, we define the variable st_. We actually are not using it. So if you would want to set the values of this st_ thingy, struct x, styf. Yeah, the other was we have not filled in. So g is also g is 7, and then the other one would be sty dot var h and I. Okay, so this is also something you can do if you want some additional structure in your structure. You could of course, as said, give it a name and then use. So if you want to have more than one entry of the same type, then you would of course need to give it a name, and then you could then you would have two things with the same content. So this thing can be done of course as well. But what we wanted to do with this union is so as you know, most systems nowadays are 64-bit, but older systems are 32-bit, and on older systems it was kind of common that you used a structure of two 32-bit numbers to represent, for example, a file of size or something that's 64-bit. So a convenient way of implementing a thing that can handle both cases, both bitnesses, like for an old system and for a new system, is to use a union like this. Struct, and we don't even give it a variable name. That changes the behavior slightly, and we have then a int value low and value high, and then we have here a int64 value. And the main and most important difference between a struct and a union is that in a struct the variables are like one after the other, while in a union all the variables start at memory block offset 0. So this is one member and this is the second member, and both of them starts at 0. At 0. Oops. As to this. So first of all we can take a size of const int. Now first of all we define a something of this thing. So my var 8 const my var 8 size is equals size of my var 8, and we see it's only 8 and this thing is 8. So as you see, it really everything starts at the same offset. And even if I would like have here other variables, it will always stay size 8, and if I write to any of those, it will effectively write to all of those. So this mechanism, in fact, is then exploited to split this value into a high and low portion without writing much code. The compiler does it for us, so to say. So for example, we have our variable 8, we assign to value 0x1 2 3 4 5 6 7 8 9 wait, let's start with 0 0 a b c d e f. That's a 64-bit number, and if we put a breakpoint here and run it and then inspect the value, then we see that here our value contains the whole value. The high portion contains, well, its high portion, and the low portion contains the lower portion of this thing, because this whole struct starts at the same offset. We could also like get addresses of those and then make the difference, and then we'll see the same behavior. So such a union usually is used if you want to make it easier for you to dissect things, or in some APIs you also use unions as parameters. So then you would have like then you would have a structure inside your union which each of the structures would have to start with the same header, so that you have one portion that is common that can be checked, where you would then check a type, and then depending on the type you would know which of the different union members of your API parameter to use. For example, the Windows kernel uses such an approach in its file request processing stack. So it's quite it's kind of quite cumbersome to use and quite old school, but it is something that you might encounter in real life more often than you might think at the moment. Okay, so what we of course also can do is we can kind of make this even more complicated. So we copy the union, let's just call it union2. And we don't need this comment, we don't need that comment. And we give this a name, so this will be parts 32. Then we repeat the same thing, parts 16. This will be shorts, and there will be more of them. So short, copy. Okay, so it will be high, low, high, and low. And of course, because it was so much fun, we can also have bytes, char, test, but we are lazy. We just use an array. And this is kind of convenient, because now you can really dissect whatever you feed into it, into its high and low portion, or its short constituents, or even just into the buffer directly and access every single character. For example, without casting. You could do all those things you do here using such a method like here, where you just take the right offset and cast it to the right type. But this is much more convenient, and things which are convenient usually help you to also avoid making mistakes. So we can here var9 value is equals, and of course accidentally this two types would be compatible since they contain the same data. Now of course if we run it, we can then see that all the parts contain the things that we expect. We can also maybe use it a bit. So let's var9 parts 32 value high is equals 0. Let's do that. And then we see here that we have cleared a portion of our integer. So this is really convenient. And effectively, when we look actually here, we also see that it is quite easily and quickly implemented. So it just uses one instruction, and to access in any of those it would be similarly efficient, because we are using machine types here as underlying types which we are using, and because as the way how this aligned, they are always correctly aligned, so it's really easy. And then just using different register names, it uses AX, EAX, or just A, or rex. Different bit widths can be addressed, and we just need to provide the right offset to the opcode. Okay, so where else such unions are useful? Such unions are, for example, very useful when creating flags. So as you might remember from our bitwise operators, I showed you how you can set and clear flags using the and or and negation operator and so on. Negation operator is called not in English. Negation operator is just a bad translation from German. Sorry about that. So using those flags is kind of cumbersome a bit, because you always need to use the not operator. If you want to clear flag, you need to write a few more operations, so it's not the most convenient thing. And likewise, with here this dissection of a 64-bit integer, we can use some similar approach to set individual bits. And even though the generated code will most likely be not any less efficient, any less long or any shorter than the code we would have written by hand, the code that we in this case need to write by hand is much less. So we start again creating a new union. We call it my flags union. And first of all, we want something where to store the data. So usually if you have flags, you want to be able to copy them with, like, handle them as one variable, basically as one parameter that you can pass somewhere. You could of course use this union type, but it's also quite convenient if you can easily cast it to something else. So here we add a named member. Let's see, int flags. So this is pretty much the variable on which you would use your and or and not operators and so on. But then we create a struct, an unnamed one, so that we can access the members directly. Let's remove this. And now what we can do, this by the way, this mechanism that will be now used inside this struct, that can also be used outside, just somewhere to save memory. So you write a type, then you write, so this thing is 32-bit. Then you write a variable name like byte1. Then you write double point, and then you write how many bits this should have. And you can really assign any amount of bits as long as it's, well, less than 32, obviously. And then you write comma, and then you write the next one, and the next one, and the next one, until you are, well, out of bits. So byte 2, let's say, oops, it's also 8 bits. Obviously that won't be a flag since it's 8-bit. A flag would be something single bit, but we will come to that. Then let's here create something that will be 4-bit. And another 4-bit. So I will make every byte a space just to make it more nicely structured. And this is obviously a nibble 5. Do I want to go with the naming scheme? Yeah, nibble 5, because it's effective. Oops, nibble. Because it's effectively the 5th nibble in the integer in our flags variable, basically. So the next one will be, of course, the 6th nibble, and we'll add a 7th nibble, because we don't need so many flags. So let's use a few bigger types, and then bit 29, and obviously that's just 1 bit wide. Should be all. And at the end you make a semicolon, obviously. So 29, 30, 31, 32. Okay, so far so good. So let's use it and see why is this so nice. So with our m var 10. Okay, so first of all, we can, because we always did it in a const is equals Caesar of var 10. So just to check that this really is just for characters, and it is, as you see. So it's really everything shares the same memory. And then the most useful thing for the flags, the most commonly used thing for the flags, is to just clear everything. Obviously. And let's see where we go from there. So we have our thing set, and now let's say we want to set the flag 31. So bit 31 is equals 1, or maybe you want to clear flag 31. Then it's equals 0, and it's a single bit, and we can make an operation on this single bit as if it would be a whole variable consuming at least 8 bit and so on. But in reality it really consumes this one single bit, and the compiler just creates all the necessary boilerplate code around this to do the same thing. So the analogous thing to this, let's just do it with another bit. Let's go with bit 32. Would be variable flags bit 32. We want to set bit 32. So or equals we want to set it so 1. We shift it by we actually need to shift it by 1 less. So we started here the numbering by 1 and not by 0, so we need to take into account that if we are doing bit shifts, the actual index starts by 1 less. So we go here with you know what, let's change the bit 39, because if I now here use the number 31, this will be confusing. So if I now use the number 30 and this and write as a comment bit 29, this will definitely be not too easy to confuse. Okay, so this is the setting of the bit, and now we want to clear it. So we remember it is and then the complement of this, and maybe for it to look better we will put this into brackets even though it's not necessary. So as you see, this and this do the same thing. Okay, let's call it set and clear, and here we'll just add also a comment set bit, but this is self-explanatory, 31 and clear bit 31. So obviously it's much nicer to write this. You don't need to think, count offsets, you just write what you want, and here that's not as pleasant. Let's okay, wait, so here, okay, this doesn't matter. 10, we already have 10. Where did we use the var10? Oh yeah, sure, here, var10 size. Zack. Okay, and now let's see what it generated. And as you see here, setting code is what? It loads into args. It bit shifts by, let's turn off the hex. It bit shifts by 30, and then it right. So okay, so this one here, yeah, set bit flag. So it loads the value from to the registry. Then it uses an opcode byte set. Currently we have a single opcode that as in x86 which already sets a single byte at a given offset, and here it does the same thing but with a byte reset. And here if we write this by hand, which kind of mathematically looks as if we would generate more code, because like we are creating basically a variable and we are using an OR, but the compiler even in the debug build was smart enough to optimize this into a single bit set and a bit clear, or rather bit reset. This is of course not true to what we wrote here, but it functionally does the exact same thing, and obviously this approach is just much nicer, even though this is just as efficient from the perspective of the code that has been generated by the compiler for us. Okay, and yeah, you can write down some more test cases for this union, maybe. So you can also initialize it with something else. What do we want? 0, 0, 1, 0f, 0, 1, 0f, a, b, a, capital F. Oops. Doesn't matter, but it looks nice if it's consistent. And let's then let's get one char. That will be the var11. var10 punkt byte 1, 12 is well 2. Then actually maybe let's do it different. Let's set this one. Let's set this to 0x AAA. Oops. 0x AA. We can get value, we can set value as we have seen already before. We can get the different nibbles if we want to, although for the nibble there is no particular type which we could address, so we need to use a character, and it will always just receive nibble 5, 12, 13, nibble 6. it will always receive only the lower portion of the variable. The 7 is equals, let's assign it to something, 0xa. Okay, we have assigned the nibble. We did already the bit assignments further up, so we don't need to do this here. So let's just run it and see how it will look in the assembler, those different operations. So we scroll up. So obviously the assignment is just one single opcode where it just writes the value directly into our flex field. Then here with the byte, it's quite simple. It just takes whatever byte we want. It assigns well, it clears the, so it uses here the EAX register, which is 32-bit, and in principle that code probably could be optimized by using just the A register name to just really get 1 byte, but I'm actually not sure if the modern version of the instruction set allows for that. It might be that it does not, because like the A is from the very early 8-bit version of the instruction set. Then you had EA for 16-bit. EA should actually already work here, and then you of course have EAX for 32-bit and RAX for the 64-bit case. So it takes it reads the whole 64-bit word for whatever reason in the register, then it masks it so that only the lowest highest, wait, which one is this? This is the highest. The highest byte, no, only the highest byte, well, it's like the first byte, so it's the lowest byte in the, semantically, but it's the first byte in the in memory that is maintained, the rest is cleared, and then it copies the thing here. But here actually already then uses the A register to tell it that it only uses 1 byte. So I'm not sure why here it didn't just grab 1 byte and then it would be able to not do the masking. But for some reason the compiler decided to do it this way. Then of course the next one was assignment. So here we load the original value. Then here we clear this area of memory, and then we have to OR it. So in this case with byte 2, it probably would be able to do the same trick like with byte to write directly, but it decided to use it to do it in a more complicated way with this clearing and setting. And then of course for the nibbles, there is no way to make this easier, so to say, because you always need to clear and to set. So here for the nibble, for one nibble we get the whole value, then we shift to the right by 10, so that will be the sorry, by 16. That will be the offset of the nibble. Then we clear everything in EAX that is not the one nibble, and then we assign it to our nibble. And then we basically do the same thing, just here with a different shift offset. So here it is 20. And then when we want to do assignment to our nibble, again we load the thing, we mask everything that we want to mask, and then we OR our nibble into where it should go, and then we write the thing back to where it came from. So this generally is how these things work. And we could also add this single bits if we want to, but in a way that will generate a interesting code, because like directly assigning values, we have seen that then it resorts just to the set bit opcode, but we could do it in a bit more interesting way. So we could have we can use character variables. Char variable 13 is equals, okay, so which one did we already use? We have 29 and 31, so we can use 30. I mean, we could of course use reuse it. I'm just trying to not create redundant code. Okay, and the other one will be 31. I think was free. Yeah, and or we use 31 for setting. We can set it. can assign something to it. We can assign, well, we can only assign 1 or 0, so we cannot assign anything. So this will be boring because we saw it, but let's do that for completeness sake. Now we can kind of reuse them a few times, but this is fine. 31, 30. Yeah, let's structure it like this, and let's see how this looks. We already had 14, 15. And let's go with 16. Yeah, let's do it like this. Yeah. Okay, so let's see. So here for the single character, it does the same trick, just that it masks it with a 1. And here, well, we do the same thing for the next nibble, so it obviously generates the same code, even though here we have written the C code slightly differently, but it ends up to be the exactly same thing. And then here we have our variable 16, so this is boring, this is just assignment, and now here our assignment, that as you see is getting more complicated. So we load the thing into EAX, then we wait, so we load the thing, is this the right thing? Yeah. We load button into our wait, scroll down. We load var 16, so our number into EAX. Then we clear, then we end it with 1, so because it's only 1 bit, so it needs to be properly conditioned. Then we shift to the left this one thing, however many we want. Then we load the other variable. Then we reset the 1 bit which we have set, and then we or the variable which we have created here in EAX with this loaded one in ECX, and then we move it into EAX, which is really unnecessary. We could here directly use ECX in this operation. Why it moves that? Well, it's not really necessary. And if you would have a release code, then that would be much more efficient. Here, just as already mentioned, the debug code tends to do things very inefficiently sometimes. Is there any other interesting case? No, I think not. Oh wait, sure, we can clear a bit. We could clear the bit so that, oops. We could clear the bit, that will be also interesting, but it will of course not be very complicated. So clear is just bit reset, so it's mostly how we already know it from before. And with the nibbles, let's see. Nibble. So we have nibble to variable, variable to nibble, that we already had more things anyways. So yeah, I think this covers everything about structures and unions. And just a hint with regard to the first homework you got, the dissection of the float and the double into the sign and the mantis and the exponent. You could have used such a union to do so. That would be quite a nifty way of doing it, because it probably is the most efficient with regard to having to write the least amount of code way of doing so. Okay, I think this is all about structures that I wanted to tell you. Yeah, since it already took the whole lecture, then we won't start functions today. Starting functions would be good, but we will start functions the next time. And let's see, is there anything I could show you that fits into the remaining 15 minutes? Yeah, there is something. So on which I already kind of even touched, the preprocessor, this in this case this pragma thing, but you have seen me using this define to define, for example, things. So let's quickly save this and create a new project, just to demonstrate this, maybe this preprocessor officially in detail, without not like kind of a thing that we just see along while we are doing things, but really so that we maybe take a look on it in full detail. So as already said, when I used it the first time, this preprocessor is generally used to you can basically use it for simple things. It is not like you cannot like write more complex code with it, but you can to some reasonable extent let's say dynamically in a way write your code inside your project, which is kind of nice. For example, like the define, which will then overwrite, or rather just be like a search and replace sort of thing. So let's start. So one thing, of course, that we are doing with the preprocessor is including other files. As I think in the first lecture I already showed you the includes. So here, just to make it more official, let's add some header 1h and the header 2h and okay, automatically. So if one thing it does here, for example, that happens automatically is that it creates for you the pragma ones, the instruction, which tells the compiler, as I mentioned during the first lecture, that it will not include things again and again, so that this is quite nice. But there is another way you could, for example, achieve the same thing, and if you browse some older source code, you will in fact see such a thing. So there will be no pragma 1, but there will be a hash if def my header 2, then define my header 2, and then endif. Then you have some things that usually goes in header, like a stroked maybe. Sorry, that should be if endef. Struct int a, int b. So the idea how this works is if this is not defined, then define it and do the rest, or don't do anything. So if we would now include this header 2 twice, the first time we would execute this, we would include basically this body, and the second time when we try to include it, the preprocessor would say, okay, if not defined but it is defined, so let's just remove everything that's in between and just have this empty text basically inserted into your file. So it this way avoids recursively including the same structure. So for example, if we in header 1 would include hash include, of course, header 2h, okay, and now here we include hash include the header 1 and header 2, then and here we make no, my stroked yeah, everything looks fine. The project should compile, and if it complains that we didn't use the variable, but that's fine. And if we would not do this, so if we forget to do this, then when we try to compile it, then it will throw an error saying that this is already defined, my struct type redefinition, because the header was included by header 1 and it was included by us directly, and the result is that in the resulting file basically, so if we would execute what the preprocessor does, we would end up with this. We remove the includes statement and we just paste in the file as is, and in absence of any other preprocessor instructions, that would be the result, which obviously would not work, since as we have seen on my many small typos that you cannot use the same name twice. That just doesn't work. You just need to always remember to pick a new name if you make examples. Of course, functionally you would not use the same names normally. Right, let's let this be commented out, and let's try this Pragma 1. And as you see here, with this Pragma 1 it compiles as well, as this basically fulfills the same function. It is just a more modern version of doing so. It basically just tells the preprocessor, if this file already has been included, then don't include it. And technically this Pragma 1 makes your compilation time marginally faster than using this approach. With modern compilers and modern CPUs, it really doesn't make a difference. But if you would have if you would be compiling something on a Raspberry Pi version 1 from 2016 or when they came out, then that might make actually a difference. So this Pragma is preferred, and it's quite a nice thing. Plus it makes your files looks nicer, because like always having this is kind of annoying. What you also people would also do with this endifs is to write in a comment to what this endif actually relates to, because if you have like then a few endifs at the end, then you won't necessarily know from the get-go which endif is for which. So if you just write it in a comment, then it will make everything so much clearer. Okay, the next thing of course we can do is define that we have already seen, I think, as well, my def 1, 2, 3, and as we have learned back then when I showed it to you first time, effectively this is just like a search my def in text replaced with whatever comes next. As simple as that. But you can make it much more complicated, because you can define my def func. I call it like a function name, but it really is not a function name. Int val, and then we can write some code. Int name is equals int val. And the thing about those things is that everything needs to be written in one line. So if you have more code, that gets ugly. But there is a trick around it. You can use the backslash, and if this is the very last character in the line, that actually also works here and everywhere. If a backslash is the very last character in the line, it means that the next line gets pulled up and continues here for what the compiler is concerned. And then let's make a second instruction. So we initialize the initial value, and then we say this is plus 1, plus equals 1. And now if we use this, then we can call it, let's say, my 1, 0. And effectively it's still a copy and paste. It takes this code here, it pastes it there, it takes initial val and pastes it here, it takes this thing and pastes it in the place of name. Yeah, and it removes that. And it generates code for you. And you can, of course, it is actually quite neat, because if you would have things where you would like have many repeatable, if you would have some code where you have to write like 3 or 5 or any amount of code lines for something, and then the same thing just with a different variable name, and then repeat it many times, maybe with some differences such that you cannot put it in an actual loop, then such an approach would help you greatly to save on time. And what we also of course can do is we can because here it like takes the whole thing and replaces it, but there is also a different way of accessing those names. Let's call them my def my func 2. I really should not call it func. My def var, my defined variable. That's a much better name. And here we will make a my defined variables file, which just takes the name, or maybe we should call it. yeah, wurscht, it doesn't matter. Int, and let's say we want the name of the actual variable, which then will be defined in the code to be I underscore name, but we cannot kind of write I underscore name because this is a name for its own, so we can use the hash name, and it will then still take name and put it in here, but it allows you to create names within the code that you create, which is not space separated. So this hash allows you to tell the thing that this will really be something from here instead of being something. So for example, we can say def hash name. Oops. And this thing, if we use it here, let's say like this for variable 2. Wait, what does it like? First of all, int def. Yeah, it needs to be consistent. Let's call it was def, so it will be def1. That should be right. What is it complaining about? Def, my def. So you see also here that it actually shows you what it generates. Like it expands to int I def1 1 2 3, and then we can of course do the same with def2. So actually, let's not remove the before use. Let's keep both, and this must be now fixed again. That was my def1. What is not like about that too? Yeah. Okay, so as you see, it is quite a powerful tool, this preprocessor. It also has a few convenience features, like for example, int line is equals underscore line. So basically, the underscore line thing will evaluate to the actual line number. So for example, if you want to throw an error message, you could make your error message include your line number and actually also the file name. What was the one for the file name? Char asterisk like file. Does this work? It must be const char. And you have also file W, which gives you the wide character version and so on. And there are also definitions for underscore I think date, that gives you the compile date, and maybe a few others, which might be quite useful if you want to throw error messages and make them contain already information lines about like where this issue occurred and stuff like that. And in C, in C++, you can make those pseudo functions things, and these definitions even refer each other. Like we saw here that this thing will here refer this, and this could also refer to something more complex. So for example, we could use this one to achieve the same goal. So here, so the name is I underscore hash name, and the initial value is my name, and this still works. So it's kind of is recursive. This refers that and that, and you can daisy chain that. You can have things referring things, and so on and so on. This works in C++. It does not work in a file which is just C. Just C is simpler. It doesn't have such a powerful preprocessor. So that is something to keep in mind, that if you just have a C file, you cannot do this more complex things. There is also a error, hashtag error. So hash if ndef. For example, if something is not defined, win32, oops, then hash error. Sorry, my code only works on Windows. Double punkt. If. And the way this works is if and def. This should be, wait, we should have win32 defined. Oh, we didn't include Windows H. Yeah, you get the error, so my code doesn't work. If we would have this defined, so if we does it really not define this by default nowadays? Preprocessor, and here in this setting, you can already define things which will be defined, so to say, in your project always. Like in this case, debug and console. If you switch to the release build, the debug goes away. It's replaced with ndebug. So we can also use this to differentiate between debug and not debug. Right, but we want to include Windows 8 so that we have Win32. Right, and now, so without Windows, there is no Win32, and we trip this error. With Win32, we don't trip the error. Because it's disabled. So it is quite a neat trick, so to say. And you could use this, of course, for many other things. So, for example, you can hash if def, or let's do. Okay, that's good. If and def underscore mx64 hash oh. So in this case, we are checking for another pre-existing, predefined preprocessor definition, the m underscore x64, which technically it indicates whether it's a Intel, no, actually it's AMD, AMD 64-bit CPU. Or we could say an x86 64 CPU. That's the most correct thing we can say. And if we switch to a 32-bit, if we really switch to 32-bit, then this error triggers. And if we add a target for ARM, like the modern thingies that you can find nowadays, new ARM64, let's copy that. Then, and if we switch here to ARM64, then it still complains that no, sorry, the code requires a Intel CPU. And of course we could do the same thing with was that? Was it just ARM64? Yeah, it was ARM64. And there is another platform definition for, of course, being an ARM, so then it won't compile on either of the Intel or AMD platforms. Or we could also go with, I think it's x86. Is it? No, it's not. I think it was E386. Also not, I don't remember. Sorry, I don't remember what's the preprocessor definition for just a 32-bit CPU Intel type without specifying just the bitness. But we could achieve the same goal even if we don't remember the right goal by using a more complex query. So hashtag if. So first of all, you can also make if if 0, then it's disabled, and if 1, then it's enabled. And this is a really nice method to enable and disable code blocks, because if you use a comment, a multi-line comment, then you cannot put another multi-line comment around it, because the end of the nested comment will break the outer comment. So that's not good. But you can have like a if 0 and in another if 0, in another if 0, in another if 0, and it will be perfectly fine. And as I think I showed you even when I showed you the some of this if stuff, that if you have even invalid code inside such a if 0 block, it will not care. It will compile as long as it's if 0 and it tells it not to touch it. But what we also can do is we can use a more complex expression in such an if. So if defined, for example, if defined this, which now is obviously functionally equivalent to if def, but here you have the advantage that you can also make a negation, and you can have a and. So if not this, and so we are now kind of requiring the platform which is selected to not be AMD 64-bit and not be ARM 64, not define this and not define that. That should be right. This is defined. The other one is not. This is defined. The other one is not. Let's screw that up. Let's screw this up. Let's do it like this. Okay, and comma. Right. So if not this or that, no, it must be this and not this and not that. If so, what we want is basically a statement that this should not be defined and this should not be defined, and then it's fine. So, and then we want to negate the whole thing. Okay. The initial code was fine. We just needed to negate this thing once more. Now it's fine. So now if it's x86, then it's fine. If it's 64-bit, this one. This okay. So this works, and this works. Now it's fine. So we can, in principle, construct such an other. If we don't know like the right value, we can just pretty much create logical expressions like in a normal if in C++. Just that we do it here in the preprocessor definition, and it's quite powerful. So we could also check, for example, if a define is bigger than something or if it's smaller than something, and so on and so on. So we can, for example, we switch this to 64-bit again so that it compiles, and then we could have here hash if my def is greater 100, so that it's true, and if then something and if we say that it needs to be greater than 123, then it won't be true, then this is disabled. So for example, this could be used if you want to check if certain header features, so if you have, for example, a library, and the library header should define the version of the library, and then you could use such things to know whether you can use certain functions that are presented in the library, or if you cannot use them because they are not present, obviously. And of course, with the debug, as I said earlier, we can have hash if def underscore debug hash and if, and then will be compiled into a release build. So this allows you to add code to your programs, which will only be executed if you are building the debug configuration, and then you can add some additional checks, crash the application on the slightest assumption that something is going wrong, and so on. Or as said, you can and as said, when you compile it then as a release build, then these things will not be a problem. Okay, I think we are already a bit over time, so I think it's a good point to stop. Just one single thing that I want to show you, which is kind of neat. We can add, we can create a file, a C++ file, SAS1 CPP, and then we have to exclude, and then let's say that, and then exclude it from build properties, general exclude from build, because we will not write something that would be, that we would want to be compiled. And then let's, for example, here we say just int x is like my def. And for this file, this kind of is invalid, but we can then, in fact, hash include cpp include source1.cpp here, and if we run it, wait, did I not have my def? My def3 is here, that should be fine. Have a typo? I don't have a typo. So effectively, this is, no, it's not. Why it is not excluded from build? Oh, I did not exclude it from all the builds. all platforms excluded from build, because as you see, it's not valid code for a standalone thingy. And then it compiles, and then we see that here when we go on locals, we have the X with the value. So in principle, you can use include anywhere in your file, and it will just take whatever you're including and paste it in there. That's obviously not something you would normally do, but there are special cases where it might be a good idea to do it. Yeah, and with that, I think we finished the preprocessor crash course. So during the next lecture, we will start finally functions, which will make us much more powerful than we were before. And that's that. Do you have any questions? Okay, no questions. Then, oh, I did not think about the homework for you. I will think something up for the next time. Today will be no homework. So let's stop the recording.